Okay, hi again, everyone. I think we should probably get going if we're going to try and get through everything before 4 o'clock. So I've started showing my screen again. Of course, this is the exercise we were talking about just before lunch. Hopefully, you've had a chance to go through it. I'll start going through what we do now and explain what we're doing as we do it. So here are the two files which we care about. We care really more about the file on the right, the module file. The left is just the program to drive it. So let's start adding in the things that we said we wanted. So to start off with, our key value type is already there. That already exists, and it makes use of this unlimited polymorphic pointer. And we also have a function to create a version of that where that pointer points to a string which it allocates and puts into kv val. So let's make sure that we can do the same for two more functions, and we're going to create those for our integer 32 and real 32 types. So we can copy most of what goes into these from the create string function. So let's do key value create I32, key and value. Let's just make it ival. Let's keep it from being value. That's result. Should be kv again, the key value pair, and I'll just close that off. And function key value create I32, and inside there, broadly the same again. Character, a deferred length string, which is going to be intent in key. And not a string, because remember we're doing an integer this time, so make it an integer, and it's going to be of kind int 32, which we've pulled out from the ISO Fortran env module. Intent in. It's not formatted very nicely. There we go. Slightly better at least. And ival. Okay. And now it's just the return type. Again, type key value t kv. And in fact, let's just copy and paste that from above. Save a little bit of time typing. So our kv key works the same way. Our kv key we can just say is equal to trim key. Get rid of any white space around that. Just get the actual characters, which means something. And then let's allocate. And we'll use this source function we spoke about, kv percentage val, and we'll say that the source for that is ival. So this means that whatever type ival is, and that's an integer int 32, is what we use to allocate memory on the heap for kv val, the unlimited polymorphic pointer inside our key value type. So that's now being created as an int 32, and then whatever value was inside ival we put into it, and that's all that we need to do. And we can then do the exact same thing again. Let me just copy and paste again, just to make sure we don't take too long doing this, for our real 32 type. So just copying and pasting. You'll see it's exactly the same, just slightly different names, and this type is a real 32 rather than an int 32. You can see, if you want to do this, it does mean that a lot of this actually turns into boilerplate. There is a way around that using an actual unlimited polymorphic class. So what you do is you say it's going to be assumed type. There are ways to do that, advantages and disadvantages. We won't cover that too much. That's very new in Fortran. I think only Fortran 2018 brought that in. So I think this is probably probably the best way to do it for now. Probably the safest as well, actually. So those are the two types that we created. So we've done that. Now we want to make sure that they will overload key value type, key value t. So let's go up to the top, and what we now need to do is we need to write a short generic interface. So we've got our three types here. Let's just write that interface, and we can just call that key value t, the same as the type. So now when we create one of these, and we say that our new key value t variable exists, we can set it equal to key value t as a procedure, and it will overload using this generic interface and use whichever one of the three constructor procedures that we created, whichever is appropriate. So key value t. And let's just put those inside there. We've already said what they are here. We can just say module procedure, as we'll call key value, create I32 module procedure key value create R32, and then the same again for the original string procedure, which we didn't have to actually write. Key value create string. So that should be enough to allow us to create them. So so these three assignments now should work. We can create three key value t's, and they should now print like so. What we are still missing are two things. A key value print, which uses a select type to say what we're going to print out from them, and then also to release that key value t once we're done with it. We haven't actually got any calls to do that here, so we can add those in. Let's quickly save that for now. So let's see about printing some stuff out. Let's go down. Was there a spot to do that? Okay, so yes, we just need key value release in here. So yeah, we don't have that. Let's go up to when we were creating things. Let's put it just here. We'll keep all our new things together. So a new subroutine, key value print, and it's just going to take in a single key value type. So type key value t, which will also be intent in, because we're not going to be changing anything in it. We're just reading from it. Before I forget, let me close that subroutine off. And inside here, we can go straight into a select type block. So let's say select type. And what we're specifically working on is we can bind here. We can do val, which refers to kv val, percentage val. So we're using this as a bound name. We're using val to refer to that component of kv. And we do end select. And inside there, we can just start doing type is. So we can say, first of all, if our type of kv val, which we're using val to refer to, is, say, the string, which was the first one we did. So we've actually say a character len equals star. We're saying we'll just assume a length for it. We don't actually know what that is. We'll just do print star kv string is comma kv percentage key, and then val, which just refers to kv val. We can do this as well. Let's also do type is real 32. What we do in that case, let's just do much the same. Print star kv r32 is kv percentage key percentage val. Again, this is slightly boilerplate in this case, but it's needed here to show to let the compiler feel happy that it's allowed to actually work with the data inside that polymorphic pointer in this way. And then let's just print out print star kv i32 is and kv percentage key comma val, and we may as well put in a default. So say class default is the sort of, if nothing else works, then do this print star value in let's say value in kv percentage key not recognized. So that's our nothing works case. At this point, I think we can actually try to compile this. So let's just have a quick go. Key value module and key value program. And I've made an error here somewhere. Oh, that's a lot of us. Module key value module. Interface key value t. For derived type and a generic interface. Oh, function must be functions. What have I done wrong? Let's take a quick look. Of course, I didn't actually put anything in here. That would have helped. I thought I had. Did I not save that? Oops. Let's do that. I'll just copy and paste this just so that I don't have to go through. I thought I had done this, but apparently I haven't. Still not happy. I've done something it doesn't like. Function key value create. I32, it's not happy. Let's take a look at I32. I32. Ah. This should have been the star, I believe. Same for this. Yes, because we aren't actually ever allocating them. We're never saying what they actually are. Does that fix the issue? Oh, we still don't have a key value release. Oh, of course. Okay, yes, so we haven't actually quite finished it. Yes, we need to write a key value release. So let's quickly put one of those in the module. Again, let's just find a decent spot. And how are we calling it at the moment? It's a yes, it's a subroutine. So let's put that in as a subroutine. Okay, so a subroutine key value release. And that's going to have just the key value itself and subroutine key value release. And this time we want to give it in-out as its intent, because we are actually going to be changing it this time. We're going to be bringing it in, and then we're going to be de-allocating its components. So we'll say, we'll put some guards in, just in case it's not allocated. We won't do anything, but assuming everything is allocated, we will actually do that. So if allocated key, we're saying, why are we de-allocating the key? It's because the key was itself a deferred length string. So this was itself an allocation onto the heap. We need to release this memory as well. So kv key, and then the exact same thing for the kv value. So if kv val has been allocated, then de-allocate it. Like so. I think that's everything we need in there. Am I missing anything? I hope not. Let's try again to compile that. Still not happy. I've allocated kv val. If allocated kv val, deallocate kv val. I don't think I've missed anything there. Key value t. I've obviously missed something. Message in the chat, maybe you've spotted ahead of me while I've been doing this. Should not be if associated. Have I? I think you're right. Possibly. Yes, you are right. That's me rushing ahead too far. Yes, you are completely correct. Let's quickly fix that. If associated, because it isn't actually an array, it's a pointer, and so we just have to say if you're pointing to something, then deallocate it. Good, a good spot that. Okay, let's see. Does that work? Looks like it does. Although it could use some helpful spacing in that print. Let's add some spaces in here just so that we can actually read things. Okay, a little bit more readable. Okay, there we go. So that now works, thankfully, although I've still missed a space there, it seems. Okay, so hopefully that makes sense. So we've done this. We've managed to have this work. We've created this key value t, where we can say that the value can be anything at all. Although we've only implemented at this point the string, integer 32 and real 32 types for it. But we can have it create. We can have it contain those and then print that information out. And you can imagine if we then wanted to say if the value is of a particular type, do some work with it. That would be fairly simple to do with the help of that select type block there. Moving just onto the dynamic list of key pairs. So this was the, oops, I need to click on that. This is the last thing to do here. So if we want to use a list of these pairs, we need to have a routine in here that expands the list as we need it. So if we go down to the bottom inside the module, so we have key value list reallocate. And that, I believe, is called from just up here. So if we have a list of these key values, which is ultimately just an array, and we say let's add a new one onto it, then it increases the size of the list that's held inside the type by 1, and then says, okay, but is that bigger than the actual list is? Is that bigger than size? If it is, then of course we can't actually store anything in it yet. We have to make it bigger. Once we've done that, then we can add the new KV pair into it. So for now, we've got to make it bigger with key value list reallocate. So let's say there are two ways to do this. But we were asked to do it the clever way, the much more efficient way. So we're going to try and do it using move alloc. So what we want to do is, first of all, let's just put in a little guard if not allocated. KV list percentage KV. And we're just going to print out a message. List not allocated. Actually, this should be a stop, actually, shouldn't it? Because it's just going to crash at this point if we carry on. No list allocated. But what we need to do, we have our KV list, and we're going to double its size. We're going to make it twice as big. And for that, we need a temporary list. So let's first of all say, let's create an integer, which is going to be nu, and that's the new size of it. This is going to be how big we want it to be. Nu, and we'll say that this is going to be equal to 2 times the size of KV list percentage KV. Now we want to allocate something to be twice as big as the current KV list. The question is what? We can't just allocate KV list itself without losing all of the data already in it. So what we actually want to do is we want to create a temporary. So let's create a new KV list. So type KV, type KV temp. So type KV type T here, and we'll just say that it's allocatable, because this is just referring to the data inside the list. We don't need to bother with the whole list. It's just the array inside here that we want to copy. And this is just going to be a KV temp, we'll just call it, and that's of rank 1. So it's an allocatable array of KV type T's, rank 1. So let's allocate that now and say, okay, allocate KV temp, and we'll make that of size nu. So this is now twice the size of the KV list, KV, and we can put that data into it. So we'll say KV temp 1 to the full size of it, so kv list percentage sign and pair. So only the first half of it, I guess, in this case, the half of it which actually exists inside the kv list original one. So kv list percentage kv, and just the same indices, 1 to kv list percentage and pair. So now we've done a deep copy, I guess, at this point. We've taken all of the data that was in here and stored it in the temporary one. Now there are two ways at this point to proceed, as I say. There's one less efficient way and one marginally, but only marginally more complex way that's more efficient. It actually isn't, it's actually a single line of code rather than a couple. The less efficient way would then be to deallocate kv list kv. So to do this, and then to reallocate it, well, not reallocate, allocate kv list kv, and you could maybe do either a source equals kv temp, something like this. You could perhaps do that, or you could just allocate it to the full size and say it's meant to be nu, and then do and then copy the kv list percentage kv 1 to kv list n pair equals the original one equals kv temp. But here, what's happening is we are allocating kv temp, copying data into kv temp, deallocating kv list, then allocating another kv list at the new size, and I've missed a bracket, and then copying data back again. So we've got two allocates and two copies. What would be much more efficient would be to do none of these and to use move alloc, as the exercise says, and we call move alloc. This is an intrinsic subroutine in Fortran, and what we do is we give it two arguments, and in that case that's kv temp and kv list percentage and kv. And what this does is it says, okay, kv temp is one allocatable array in this case, and this is another allocatable array. What we're going to do is we're going to take the array in memory that the first one points to, and we're instead going to move it over to the second one. Whatever the second one, so kv list percentage kv was originally pointing to, we lose it. So this is now pointing to nothing. It deallocates its original array, and then it gains whatever array this was pointing to. And this array is now left pointing to nothing as well. So this one is now unallocated. But if we do this, we only do one allocation and one copy. So it's much more efficient, and as your arrays get bigger and bigger, this becomes a much faster way of changing the size of your allocatable arrays. Okay, hopefully I've not missed any brackets or anything there. There's a decent chance I've missed something. Let's try to compile that, and I've still got something wrong. Used to type an object. Oh, someone else is way ahead of me. I'm glad someone is. What do I use? Size instead of n pair. Where is that? Sorry. Oh, you could okay, yeah, you could have done that. Should be key value T, not KV type T. Very possibly, yes, you're right. Key value, key type T, key value T rather. None of these types I'm writing about actually exist. Okay. Yeah, but yes, Mark, you're right. Yes, this could have been n-pair. There are multiple ways of doing the same of it here. It's essentially equivalent. Okay, thank you, builds. Thanks for being good checkers of my code as I'm writing it. Okay, and that works. But what we could, of course, do is we could add some code in here to demonstrate this. Do we have any driving code? I think let me quickly open the solution, and I think I can just copy some code to show. Yes, okay. Let's quickly let's just quickly add some like a KV list in here. So we've created a KV, a key value list T called a list, and we can just let's just try and do all of this. Just copying and pasting some driving code from the solution in. Oh, and of course we need to actually create it. Okay, good enough. Good enough to hopefully show it's running. Okay, and if we run, stop, no list allocated. I think this is because we need to create it with some initial size. As this code gets more and more complex, it's a bit harder to debug live. Going back and forth. Yes, I think it's because it's created with a size 0 up here, and then we're just let's just for the sake of it, just for the sake of it, if I change that. No list allocated. Okay, I think I'm just calling it wrong. I think I'm missing something on the left-hand side here. Hopefully, though, hopefully that demonstrates most of what I really wanted to get at. These solutions are in the directory and contain all of this, and actually a little bit more that we haven't spoken about. So if you are interested, I would say please do take a look at that. Really, the important things are the way that we use the overload, I would say, to create the different types, and then using the print function to make it general how we deal with the various values that can go into our pointer here. Okay, I'd like to move on because the last section on C is fairly big and we're still heading towards that, but are there in general any questions about this? Otherwise, I'll leave this for you to experiment with in your own time. Any questions just now? Okay, I hope that means everyone's okay with the general principle that we're using here. Um, Again, yeah, these bits of code are a little bit chunkier, a little bit harder to get through in the time that we have. Okay, I'll move on then. The next two sections are comparatively simple, so we hopefully won't spend too long on these. And then at the very end of the day, we'll be, of all things, doing some C as well as Fortran. Okay, so moving on to type parameters. And this is a little bit, just a bit like using templated types in C++, just a little bit. And it's also a little bit like adding arguments to your types. So just to build up to this, so of course we just had in that exercise just now. If we use the ISO Fortran env module, then we can get kinds like int 32 and real 64, and make those available for use in a way that means we can take our code anywhere at all to any system with any compiler, and be sure that when we ask for a single precision real, for example, we do actually get a single precision real that matches the ISO standard. But this is, if you think about it, this is kind of like we are parameterizing our int. We're saying, don't just give us an integer, give us this specific kind of integer. That kind of you just sort of accept as normal while you code this, but we'll see how we can bring this into our types as well. And similarly, if you put brackets after a character, you can say, give me a deferred length string, or give me an assumed size string if you put star instead. So again, we are adding parameters onto our integer and characters here, into these two intrinsic types, but we can do this with intrinsic types in general. But following this same concept, we can parameterize our own derived types, again by just putting brackets after them. So if we have a type that we've created, let's just call it my array T, then we just add on this new bit of syntax, brackets after the name of the type. Let's just call it kr and nlen. And what we're doing now, we have to put them into our type. We say kr is a kind, nlen is a len. Then we can say create this as a parameterized array of reals. So our kr, a kind, we're saying use that as the kind for our data. So this will be an integer. Remember, kinds under the hood, although we refer to them with names like int 32 and real 32, they are actually just integer values. So pass that through, treat it as a kind, and use it to say what kind our data should be, what real kind. Similarly, nlen, we give it this len at attribute, and then we can use that as a length to say how big that array should be. There's something to think about here, a couple of, well, one restriction and one thing to just remember, that is that a kind in particular has to be a compile time constant. So this can't be a variable. Kr has to be something that the compiler can determine statically, because it's either coming from a parameter somewhere, or it's coming straight, say, from the ISO Fortran env module. So a kind has to be known at compile time it has to be constant at compile time. The length, this can actually be deferred until runtime. We'll see a little example of this in just a second. The extra components, so they do act as normal components in that we can give them default values. We just specify those here. Again, we'll see an example of that. And again, you can access them with the percentage sign again. And that's part of why they're still here. Although we've just used them, it's sort of obvious, I guess, in a way, how KR should be used just from this one line. We do still make the effort to say here what really are they, and then that also gives them names which we are able to use to access them when we're working with them. When it comes to actually using them, then you might do something like this. So if we want to create a myArrayT, let's just call it A, we just say type myArrayT, and in this case, we're going to use a real 32 for data. So we want a single precision data array, and it's going to be len input. And len input can, as I say, this can be anything at all. This could be something read from input on the keyboard. It could be read from a file. It could come from anywhere. It doesn't have to be known until runtime. Unlike the kind, which really does have to be known at compile time. If you want to, you can also give it an actual argument like this. So you can pass nlen equals star through. And that's just like if you say do an assumed size for a string, in which case you're saying, okay, let's just say that A shall have whatever size it ends up with. Just create it with whichever size the data is. If you did it with a pointer, then you would instead defer it with a colon. So nlen equals colon. That broadly matches the way that that colons are used to defer shapes or sizes. We saw that happening a little just now in the exercise from a minute ago. And in this case, also, just to be clear, we've also provided a optional keyword nlen. We didn't have to do this, but we've just chosen to. So just to finish this off, there's an example code here. This is actually in the directory. Maybe we could take a quick look at it, but I'll just show it's running in a second. So it uses ISO Fortran env to give us access to the kinds in it. And then there's the myArrayT, which works just the same as we said now. We haven't even bothered here to put it inside a module or anything. We just put it straight in the example one program. Integer kr, okay, and then type. We've just said let's just create a type myArray. And printed out what those are. So we've put in kr equals real 64, nlen equals 1000. Just print those out, and then we do a little more. We then actually get a new value of nlen from the command line. So we actually ask in a prompt for the user to enter a number. Then we call this subroutine defer me, because in here we have deferred the creation of a myArrayT. So inside here we create a myArrayT, which we're calling B, and that's using the value for that length that came straight from the command line prompt. And when we do that, we can then create it, and we'll see here that it does actually get the shape that we thought it would. So if I just quickly quickly show this. Let's go down into section 12. Example, let's just quickly show you. Example 1 should look just like that. Yep. Oops, we don't want that. Have I? Kind? Yeah, that's wrong. I'll need to fix that in the. Actually, I think that is fixed in the repository. It's only nlen which we want. Yeah, so this, let me actually just copy and paste this whole thing. I think I have fixed this, but my clone of the code is not quite correct. Okay, I think that's hopefully a bit better. And if I run that, okay, it asks me for an nlen. Let's just say, give me a size 200. Yeah, there we go. So created the first one, but then when asked for nlen, I said, give me a my array t, and just use the parameter that I gave it at the command line, nlen, and that was parameterized and passed through to my array tb when it was created. Okay, are there any questions about this? As I say, it was a very short section, and I think the next one will probably be even shorter, and then we'll just finish up with C. But are there any questions about parameterized derived types? Okay, I think people are happy with that then. I don't think there's too much controversial there. So just a short section on intrinsic modules. So we've been using this, and I think we spoke a little about it as well on Monday, how it's a useful module to use. I think particularly for your kinds, if nothing else, it's good to know when you're creating your instance and reals that they are actually the standard conforming kinds, which are going to work the same way everywhere. You aren't going to go to a different system or use a different compiler and suddenly find that your reals or double precisions suddenly have half or twice as much precision as you thought they ought to have, and suddenly everything's breaking because of that. If you use ISO Fortran and get your int 32 real int 64, real 32, real 64s from that, then you're guaranteed that your code will always have will always work numerically in the same way in terms of the IEEE maths. But there are actually 5 intrinsic modules. The other 4 are split into a group of 3 and then a group of just 1. So the other 3 just then are all related to IEEE arithmetic, IEEE arithmetic itself, IEEE exceptions, and IEEE features. One which we'll talk about next lesson, right before we finish, is ISO C binding. So we'll leave this one aside for now, and instead we'll talk about these 3. What you can do is you can always add the optional intrinsic attribute when you're using a module, and this gives you a little bit of flexibility in case someone has, either you or someone else has created a module which has the same name as one of these intrinsic modules. That would be, I would say, a little bit risky if someone were doing that. I wouldn't recommend doing that, because you're probably asking at some point for someone to use use either or one of those intrinsic or non-intrinsic modules and accidentally getting the other one instead. Maybe there's a good reason for it, but I think most of the time you would avoid using these names again pretty heavily. But if you do actually include it, you can always be sure. If I use intrinsic ISO Fortran env, then you're always sure that the ISO Fortran env I'm getting is the one from the compiler, which is defined in the Fortran standard. I'm not getting some random other module which just happens to be called ISO Fortran env. And if you wanted to go the other way around and say, yes, I know that there is the intrinsic ISO Fortran env, but I want my own ISO Fortran env, you can put non-intrinsic on there and it will favor that. Generally, so best practice, something which we haven't done, is to use an only clause with that. And I think we did speak about that. Was it earlier on today or on Wednesday? It's good practice to do it. It's not something you have to do, but it's good practice to just only bring in the names from these modules which you actually need. It helps you keep a lid on what you're using or not using, and it makes sure that names for things like real 64 are available if you don't actually use them from the module itself. Yeah, and that does actually apply to your own modules as well. It's a good idea to only bring in the things which you actually know you want. Okay, so let's just go through these modules one by one, these four intrinsic modules about the ISO standard. So ISO Fortran env gives us several things. So we've spoken about those kind types that it brings us, which are very, very helpful. But it also includes units, so error unit, input unit, and output unit, which make sure we can always refer to, say, standard out or standard error without having to worry about which logical unit values, which integer values our compiler has chosen to use in its implementation, because that's not going to be the same. And I think I do get the chance to show you in a second how Fortran, G-Fortran and Cray Fortran do this differently. It also brings in error codes, iostat end and iostat EOR for end of file and end of record if you're using record-based input-output. And more stuff related to input-output, character storage size, file storage size, and numeric storage size. It brings in all of these in case you need them. It also provides functions, so you can use compiler version and compiler options to return strings which contain information. Those are fixed at compile time, so it makes sense. You have to run this at compile time, so the compiler options are a way, say, it can help with repeatability. If you've got a numerical code, it can be helpful, say, to know exactly which options the code was compiled with when you're looking at your results and you see, okay, I got this performance. I got this performance. Oh, it looks like this time it ran twice as fast as it did before. I wonder why. Well, if in your output somewhere you print out, say, your compiler options or maybe your compiler version as well, then you can see how the code was actually built in each case. And perhaps you see, the case where it was twice as fast, it was using O3 optimization. When it was really slow, for some reason, I was debugging it and it had O0 or O1 on it. So that this can be helpful for repeatability of simulations. Yeah, this very quick example, ISO Fortran env. Let's just take a quick look at that. Super quick. I think this is the only thing we have in here at the moment. Okay, so at the moment I've got the Cray compilers loaded. So if I just ftn print ISO Fortran env.f90 and then just run that, we can see some of these numbers. So these are kind of helpful. A lot of the kind types you find are actually fairly constant across compilers. So these don't change too much, but it's probably still best to always use them from the module, just to be guaranteed that you're always getting the value which the compiler interprets in the right way. What does often change are things like the input-output units. So so Cray, as we can see, if you were to do print to a write to unit 101, you'd be writing to standard out. If you were doing a write to unit 102, you'd be writing to standard error. If I quickly load the GNU compilers and recompile and then rerun, these have changed. In fact, a lot of these have changed. The IOStat and IOR, a lot of these have changed, but I think the ones which people find themselves running into the most, as I say, are these units. Now, output unit is 6, error unit is 0, input unit has also changed. So if you were writing code and for whatever reason you had hard-coded a write to error unit 0, sorry, to IO unit 0, intending that to go to standard error, that would work fine with Fortran. If you then took that same code and compiled it with Cray and ran that, then in that case, unit 0 isn't on here. What you'd actually probably get is a file called fort.0 being created, and whatever you had put in that write would go into that file instead. So hard coding these units in is not a good idea. What would be much better, much preferred, would be to use these from ISO Fortran env, and that's where you can go from Cray Fortran to G Fortran to NVIDIA Fortran, Flang, whatever, and it doesn't matter what integers, what actual values are underlying each of these, you still get the right thing as interpreted by the compiler. Okay, moving on. There's not a great deal left, just a tiny bit here. IEEE arithmetic support. So these are really the other three modules, and there's a huge amount in these, and they're, I'd say, a little bit more specific in their use. It's worthwhile, again, remembering not necessarily everything that's there and how to do it, but remembering that these modules exist, and that if you do happen to need this this functionality, you can go and read the docs for them and then use them. So IEEE exceptions gives you handling for things like underflow, overflow, inexact, although might be best to avoid that one, invalid, divide by zeros, and so on. So if your math starts churning out errors like this, you can maybe use this module to help handle that. IEEE arithmetic gives you functions for doing things like identifying negative infinity and so on. And it actually acts as an extension to IEEE exceptions. Finally, IEEE features doesn't actually include things which you would use in the module, so use in your code. It doesn't provide parameters or procedures for you to use. But instead, if you use it and bring something in, so in this case, IEEE subnormal, then it makes sure that when it's compiled, that code as built must support subnormal floats. So, say for example, in this case, maybe you have an algorithm which is very susceptible to underflow. In this case, you'd say, okay, give me let's just make sure that we have subnormal maths enabled whenever I build this, to make sure that we actually get gradual underflow and not just everything hitting zero. So so they're a little bit specialist in their uses, but at the point you do need them, they're very helpful. So as I say, it isn't necessarily something you'd want to remember like a textbook in your head. This provides all of this, this provides all of this, and this provides all of that. And I remember how to use all of them because there's quite a lot. But it's worthwhile just remembering that they are there, and that if you're running into something where maybe you do need to start checking for divide by zeros or using subnormals, then you can come here and turn these on and use them. Okay, and that's actually all we have in this section. Again, these past two ones have been quite short. We're just sort of talking about little useful things that might show up here and there, things which are good to bear in mind. Are there any questions just now about anything we've just covered? Okay, I think that's a no. So, assuming everyone is happy, we'll carry on, and this is the very last section that we have to go through. It's fairly long, so what I'll do is I'll actually make a little start on this, and we'll carry on until about quarter to 3, and then we'll have our 15-minute break, and then we'll come back after that and finish it off before 4 o'clock. So so this last section, as I said, we're talking now about how to use both Fortran from C and C from Fortran. We'll actually do that the other way around, what I just said. So we'll start off with looking at how to call C from Fortran, because that's a little bit easier. Calling Fortran from C is a little bit trickier the other way, and Fortran 2018 has actually updated this quite a lot. So we'll try to make it fairly simple, but we are getting a little bit more complex here. And I should say, of course, that since we're talking about Fortran and C interoperating, it might be that some of you or all of you maybe even have no interest in C and never want to use it. In that case, I would say don't worry about it. You can just kind of absorb maybe the basics of what we go through here, and maybe again just remember it can be done, and come back here in the future if you ever find that you actually have to do it. But for those of you who do use both, this may be helpful. This is also sometimes particularly useful if you're trying to couple different codes together. This is where this can come into it can really come into its own. So so Fortran brought in this idea of what it calls interoperability operable entities, which are types and bindings which have their data set up in a way, their data set up in a way, or their call signatures set up in a way that C is able to understand it. So we're kind of talking about Fortran bending itself to work like C in the background rather than the other way around here. And because C and C++ are close enough in the way that they work, you can also use this to have Fortran talk with C++. And to do this, we use that other module which we mentioned just a few minutes ago, ISO C binding. And what this does is it gives us a lot of extra types and some extra functions and subroutines to make this all work. So for our integers, reals, and complex types, we now have to add a new kind parameter that says, okay, set this up in memory, create this this integer in this case in memory, such that we can pass it straight through to C without having to, start mangling data behind the scenes. So depending on what type you need it to be equivalent to in C, you basically just do C underscore and then that type. So C int, C short, C long, C size T. What you can do is you can check the actual values being used there. You can see which integer values each of these kinds actually is. And if you get a value of -1, then that means that at least in this Fortran compiler's implementation, there isn't any interoperable Fortran type that would work with the corresponding C type. If you get a -2, it means that there is no C type which would work for what Fortran can provide. This one here, C size T, that's usually an unsigned integer in C. C only really specifies that it has to be able to provide a number at least this big. So it's usually a size, an unsigned integer, just to give you that extra bit of range. There isn't any actual corresponding unsigned type in Fortran, so what it'll probably do is it'll just actually create a signed type and do and make that work behind the scenes. For reals, again, very similar. If you want a C float, then you ask for real C float, real C double, real C long double, corresponding to each of those in C. If you get back a -1 on your type, if you actually check it, then that means that that Fortran doesn't have a built-in type and an intrinsic type with a precision which matches the C type. Where that can happen is long double here. You can have other negative values. Of course, reals are a bit more complex than integers in the way they work. So there are more reasons they might go wrong. So really what you might do is you might, if you wanted to be good and check beforehand that your code will actually work, you take a look at what these values are. If C float, if C double whatever is less than 0, probably stop your code and print out what that value is, that negative value is, and go and check what it is and see if it's something which you can work around. You even have complex types, so you can go for C float complex, C double complex, C long double complex, and those precisions just match straight back onto the real types. There's a single interoperable logical type, C bool. So this might actually end up being a logical. So this might actually end up being an integer again behind the scenes. So we've got a small bit of code. We'll just take a quick look at this. Again, we'll check it out with both compilers. Print ISO C binding. So let's go down into 14, and let's do which module do we have? We have progenv GNU. So let's do ftn print ISO C binding and just run that. And we've actually got types for everything here, and actually most of these types actually correspond pretty well to the intrinsic Fortran types. So you could check these against what we had up here. Int 8, int 16, int 32 were 1, 2, and 4. That's really what we've got here. We've got a size 2 for C short and a kind of 4 for C int. So that's actually working out pretty well. If we did module load progenv cray, let's just see what the situation looks like there. Compile and run. We do have a difference here. So what we don't have are long double and long double complex. The reason for that probably here with the Cray compilers is that the Cray Fortran compiler is a little bit sort of divorced from the Cray C and C++ compilers. So Cray used to write all of these completely from scratch on their own, but maybe 5-ish, 6-ish years ago, maybe 2019, I'm not sure. Cray actually began to move to using LLVM Clang as the basis for their C and C compilers, whereas Fortran is still their own in-house, I guess, built from the ground up by themselves compiler. So converting types between those two fairly different compiler code bases is going to be a little bit trickier. So most of the functionality is still there, but if you are working with the Cray compilers and wanted to use C long doubles or long double complexes, then you would have to either go to a different compiler, G Fortran in this case on ARCHER2, or you'd have to work around it in some other way. Okay, it's now 2:45. So I think what we should maybe do there is just take a 15-minute break, and that'll be our last break of the day. When we come back, we'll start up again with this section on C interoperability, and yeah, push on towards 4 p.m. when we will aim to end. Okay. I'll see you back here then at 3 o'clock. Welcome back, everyone. I hope that was a nice wee break there. Let me share my screen and we'll carry on and do as much as we can before the session finishes. We'll aim to try and get there by 1600 4 p.m. Okay, so we've just been seeing how the numerical types and Boolean types work when you're interoperating between Fortran and C. What about characters? So we want characters to work as well. we expect that to work, and it looks something like this. Character kind equals C char, but len equals 1. This is a little bit different. So what you have to do when you're passing strings back and forth between Fortran and C is remember that in strings, really think about them as being assumed size arrays of characters, each being len equals 1. So this is just moving a single character. We can't really move a whole Fortran string across as is. Instead, yes, think of them as being arrays of len equals 1 characters of kind C car. Something else you do need to think about are the C special characters, in particular the null character. So we've got C null car, C alert, C backspace, C form feed, C new line, C carriage return, horizontal tab, and vertical tab. All of those mean things in C. They don't really mean so much in Fortran. So we have to provide these special characters through the module to help us treat them. Of course, when you get a string back from C, it's going to finish off with what would be in C the null character, the character that tells C this string has finished. It's over, and that's going to be visible to us in Fortran in a way that it isn't in C. So what you might want to do when you get that string from C back into Fortran, and you see it's actually one character, probably longer than you were expecting, that's because it's tagged a C null car, which is equivalent to \0. That's been tagged onto the end of it. You'll probably, now you're working in Fortran again, want to get rid of it. Okay. So now we know a little bit about the types and how they move back and forth between Fortran and C. We can think about how to actually call C from Fortran. We'll do that using one specific example that also lets us see how to work with strings, and that's A to I. So this is in the C standard library. It takes in a single string pointer. So this is remember, a string in this case is really an array, which really means it's a pointer in C terms. It's just a chunk of memory, and we get a pointer to say where it starts. That's how different strings are in C. So it takes in that string, and what it returns is any numbers inside it that it can convert to an integer as an integer. So for a very simple example, if you passed it the string 123, you'd get back the integer number 123. If we wanted to call it from Fortran, what we need to do is we need to write an interface. It kind of feels at this point like about a third or a half of this entire course has just been about writing interfaces of some kind, and we have to do that again here because we want to tell Fortran there is an interface out there, that there is a procedure, in this case a function out there that I want you to use. This is how I'm providing a contract of how it works. This is how I'm going to guarantee to you it works. So we say interface, end interface. It isn't generic or abstract or anything. We're just saying there is an external function out there, because this is a function, and it works like this. We'll give it a name, C underscore A to I, but we could really call it anything that made sense. And it takes this as its dummy argument, and it returns the result I. That's going to be our integer that it brings back. There's a little extra bit of syntax in the middle, which is bind. So we're saying that we're going to bind this this C A to I function in Fortran to the external C function called A to I. Within it, we have to say what types these are. So we're going to use the intrinsic ISO C binding, only C car C int, to say what kinds they are. We need to make these available for use inside this function in the interface. And then we just say, okay, character. So C is a string, as we say, is going to be an assumed size array of len equals 1 characters of C car. That's going to be in 1010. We aren't going to be changing anything to it. That's what's going to happen to it. And then we're getting back from that as our result an integer of kind C int. And at that point, we can kind of just go ahead and use it. Yes, just to note that if you don't give it a name here, then the compiler will assume that the actual name of the C function that it's trying to bind to, that it's trying to use externally, will have the same name as the function that you gave it here. So if you want to give it a different name in Fortran to the name that it had in C, then you need to give the proper C name here inside the bind. Once you've done that, though, you can just go ahead and if you've got your C int ready to take the result in, then you can just call I equals C A to I, and there you just put the string that you want to pass through to it. Something to note is that, of course, in C, the concept of subroutines as such doesn't exist. Instead, you have void type functions which probably have or may have side effects, but there's nothing that you just call in the same way that you call a Fortran subroutine. So so if you do have a C function which is void, then you actually declare it as a Fortran subroutine. There's something else to take into account, and that's the different parsing mechanisms between Fortran and C. We said early on, I think on Monday, that that Fortran does something that looks like pass by reference, but actually isn't. It's actually sometimes allowed to be copy in, copy out. Whereas C's default is to pass by value unless you use pointers specifically to pass references to the memory in and out of your functions. So by default here, you're going to be passing this by value. And that means that we have to tell Fortran when we use a function in this way, when we bind to a C function like this, that it should do the same. So in our binding for it, most of this looks like what we had up here for C A to I, binding against A to I. But here where we're binding C hypot against the actual C function hypot, we need to tell it that X and Y in the C prototype here, they aren't pointers, so these are being passed by value. We have to tell Fortran that it should do the same thing. So in the interface, when we tell it about X and Y, we say, okay, real CW, and we give it value here. So that's kind of the same thing as intent here, and it doesn't actually replace it. But if we don't have that, then that means we are going to be giving it a pointer. So that's actually what we were doing by default here, because our const char star string in C is a pointer because it's an array of characters, then when we gave it the string, the string argument here, we didn't have value on it because we were doing the same thing. What we were actually passing through to the function wasn't the string itself, but a pointer to its location in memory. So it's something that you have to remember to do. If it's passed by value, which is default in C, then you have to add value onto your dummies in your interface. And you can actually, just as an aside here, yes, you can actually use that outside the context of working with C. You can just use it in normal, pure Fortran and indicate that the dummy argument should actually be copied in. So you can get basically a brand new copy of that variable with the same value to work within the scope of the procedure, and then those changes won't be seen on the outside once you're finished with it. Okay, so with that being done, we'll start our first proper exercise here. 10 minutes we have for this, although this is actually fairly long because this one actually needs you to write a Fortran program from scratch. I think what I'll do is I'll give you the full 10 minutes here, and then I will probably just walk through the Fortran solution rather than write it myself, because it's long enough. I think it probably would be more effective to walk through it that way. So so let's imagine that there's a C function, and this does exist. It's given to you. It's in a file called smprintf.c, and there are actually two of these. You're given a csmprintf float and csmprintf double, and both of these wrap the C standard library function smprintf, which takes a float and writes it out to a string with a given format. You also give it the maximum number of characters to write in this NSZ. The string is put into string, and what you get back as the integer return value is the number of values that actually were written to the string, not including that final \0 null character. So those C functions, the float version and the double version, are given to you, and you can compile those to an object file, to a .o object file with this -c flag. What you'd like to do now is to write a Fortran program from scratch to use this. So maybe what you can do is you can think about writing the interface to that. You can think about writing one each, and it should be fairly simple to do one and then copy it and use it for the other, because smprintf float is going to be basically the same as double. The only thing that changes is that here float x becomes double x. And then set up some variables with interoperable kinds, put some values into them, and then just see, can you call that function? I would maybe, if you want to go through things quickly, maybe just try doing it for either the float function or the double function. So you should be able to see it here. csmprintf. So if I just quickly open csmprintf, you'll actually see it's very, very short. All it does is say, here's the one function, And in both cases, we return smprintf. It's just that the one prototype has float x and the other one has double x. So if you start off writing some Fortran code using what we've just learned to just do one or the other, and if you want to try both, you can do so. In case you aren't familiar with C and you're wondering, okay, what on earth is a good format to give it in order to print out either a float or a double, you can just try and use one of these. These should give you decent looking output according to the way C formats work. So you compile this to an object file, and once you're done writing your own function to do that, then you can compile it against that object file using this command here. And if you're interested, take a look at what length those strings are. So what length you told C it could be, and then how long does it say it actually is according to the return that value from the function itself. Remember, it returns the actual number of characters used. And then what does Fortran say? How long does Fortran say the string is, and are they the same? So I'll give let's go up until 25 past. I'll give you that long to just quickly try out one or the other, or if you're very fast at this, you can have a go at both the float and double functions, and then I'll show you how we can how this works in the example solution. Okay, just about 10ish minutes, about 25 past. I'll start doing that. Hi everyone, I hope you've been able to have a quick go at that. Let's see how it might be done. So, as I said, in the interest of going quickly and not spending forever typing things out, I will just copy from the solutions the example program into the same directory. Let's just quickly take a look at what's going on inside it. You may have taken a look yourselves, of course. If you've been trying this yourself, hopefully you've got something similar. So nothing fancy in the way we've set our program up. We've just called it example 1. We have our ISO C binding kinds, which we've brought in through use ISO C binding only. So we've got integers, characters, a size T, float, double, C, null character, because we want to do something with that. Implicit none, of course, and then our interface. So here we've got the interfaces for both of those C functions, both C smprintf float and C smprintf double, and we're binding those against the Fortran name of f smprintf float and double. Other than that, though, they're actually both identical, names aside, with the exception of the kind of their x argument. So x here is a C float, and x in the double is, of course, a C double. That makes sense. Both of these C smprintf float and double are there sitting in that C file. So we should have access to both at link time. It's just a matter now of actually using these to do something. So then we set up some variables, and we're using the interoperable seed kinds for all of them. So we've said that the size that we pass through, so the maximum allowed length of the string that we are creating is 80. That's with the C size T. We're also saying that's a parameter. It's a constant value. That's just a choice that we've made here. And then we've said let's have a kind C car string, and that's what we're going to be putting our written string into. So we've said that this is a string of this size of SZ size equals 80. Then we have our format string. We've just given that a length of 10. And then just two reals C float for the one case and C double for the other. And we've just put some numbers in those. Numbers you may recognize. Finally, we have an integer C int, and this is the return from the functions. How many characters were actually written into the string. So we do the same thing in both of them. Again, single position and double position. We're copying a lot of code here. We've just got a different format in each case. These use the formats which were suggested in the example. So we print out the format and then we make the actual calls. This is where the interesting stuff happens. We pass those values through string SZ trim. So we do trim the format down to remove any white space around the format which we've actually placed in it. And X itself. X is the number which we're going to be writing into the string. And then we get back from that the return value. So when we run this in a second, just to be aware, the return value, remember, is how long C said the written string was. How many characters did it actually write into the string? What we then get is a little bit of logic here. We ask Fortran, okay, where in that string did it place the C null character? And then we ask it, what did the string look like, and how long was that trimmed string? And we do that for both of them. So let's just give that a quick compilation now. So let's say let's compile the C code to object only, and that gives us C snprintf .o, and then let's compile C snprintf o against f snprintf.f90. That should build, and now if we run that, that's worked. Okay, and this seems to have worked correctly. So here's our single precision results and our double precision results. In both cases, we're getting the correct string back, and it's been formatted according to the format string which we gave it in each case. The interesting thing is in that null character again, which I've been talking about. So if we look at the single precision results here, the return value that we got from C was that it had written a string of 10 characters. Of course, that includes all the white space. When we ask Fortran where is the null character, it's at position 11. And then if we ask it to print the string, taking off any leading white space, we get this for our string itself, and we're told that it has a length of 11. So we can't see that null character. It doesn't print out to anything in the terminal, but it is there still. Fortran sees it as an extra character. So this is where if you were doing this back and forth of strings between Fortran and C, you would probably at this point choose to only actually use the first 10 characters in this string. You wouldn't bother with the 11th null character, because in Fortran it doesn't really have any meaning. And the results are the same for the double precision run. Okay, any questions about this before I move on? Or is everyone happy with that? There is a little bit of discussion here. a point to note, something you might ask, and I have been asked it in the past, and we spent a lot of time on this when I was teaching this last year with another one of my colleagues, is couldn't you create a generic interface for these two functions? If I just quickly open up this again, we've asked, could you create an FSN printf, if you like, which is a generic interface to overload both this and this. And it seems like you really should be able to. But what we found with every Fortran compiler that we tried is that every compiler says, no, I can't tell the difference between them. And we think it's something to do with the way that it binds them. This muddies the signatures here. So the way that you'd actually do it to work around it is you would then write another level of Fortran wrapper functions, and each function would itself only call this or this. And they would do that by taking in Fortran native types, so using Fortran native kinds in their type parameters, in their kind parameters, and then converting those to the C types, C size T, C's double, and so on, and only calling them at that point. So you have to overload at a purely Fortran level, and only then, once you've done that overload, can you then start delving into the C. It's a little strange. We couldn't really work out if that was an accurate interpretation of the standard. It was a little bit vague, but it's an interesting point. Okay, it's also worth talking about arrays here. So passing arrays back and forth is perfectly possible as long as they are of non-zero size. We did say on Wednesday or Monday that C arrays cannot be size 0 because a C array has to point to has to be a pointer to memory, whereas a Fortran array is a real object of its own, which can say, I exist, I don't have any memory to point to, I'm just a size 0 array. So we can do that as long as we have a size of it that isn't 0, because that wouldn't mean anything to C, and if it has either an explicit shape or an assumed size to go with it. So what you might have is, say, this C function. This is void. So remember, this is going to turn into a subroutine in Fortran. In C, it's a void function, and in this case, we're saying that we are giving it an explicit size with int n-len. So it's a double array of size n-len. And then you'd write your interface for it like this, passing through integer C, int value, passing this by value because it isn't a pointer, so it's just being passed by value. And for double data, we don't put that value in because it is a pointer. We are actually pointing to real memory, and it's that pointer which we're passing through to the C. Real C double, intent in out, because in this case, C is the C array 1 function is going to be taking double data in, taking that data, doing something to it, and then passing control back to us to do something else with it. And here we're being very explicit again. We're saying that that array is of size n-len. That's fairly simple as long as your arrays are all rank 1. Of course, rank 2, it gets a little bit messier in C. So we need to now remember specifically that the ordering of those indices in memory changes. There's definitely a lot. There's some things to think about here. What's important to remember is that the memory itself that you're passing through doesn't change at all. All that's changing here is the way that we index it. So where in Fortran for a rank 2 array, we might have an integer of an integer cint array, and that's rank 2. Indices, well, sizes here m and n. Then inside C, we would refer to that like this: array bracket 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 m, or array bracket n bracket m, to be. We would have to do that to be interoperable, to make sure that we can access that array and move through it correctly. So you would work with this this array like so in the Fortran, and then to correctly convert its indexing for use in the C, you would just either replace one of those. You would replace the last index with a star if you were going with this for your C prototype, or if you were being explicit rather than assumed size, then you would do array nm, and that would be declared as dimension mn inside your Fortran interface. So there's a little exercise here. I think given it's now 20 to 4, I think what I will actually do is just directly show what this looks like. Go straight through with the demo here and show how it works, rather than spend time on this. I hope that's okay. I'm sorry that we're running a little bit out of time, but I really don't want to keep people any later than we said we would keep you. So what we have are C array.c. Again, just a very short bit of C code. And all it's actually doing is looping through the array that we pass to it, and it's declared in what would be in the equivalent in Fortran an assumed size array. So we're saying its first rank in Fortran, or its last rank in C, equivalently, is of size mlen, and its last rank is just of whatever size it gets. So then we loop through it, and we're going to loop through in C order, where the last index changes fastest, and just print out each element in turn. So if I copy, let's copy from the solutions farray.f90 here, and then I'll just show you what the solution, how the solution works alongside the C code. Okay, so on the right is our C code. I'll just keep that open as a reference. And on the left is the Fortran. So we actually create a module to work with this time. And in there, all we do is use the ISO C bindings and create the interface. So here's our interface to C array. We say that it's just going to have the same name, so we call it C array in both Fortran and C here. It's only using C ints. That's fairly simple. And we say that its first two dummy arguments, mlen and nlen, are both intent-in value passers of C ints. And then the array, the interesting part, I guess, we're saying again is assumed size. Integer kind cint, intent in, idata mlen. And you can see, so we've put idata mlen comma star, and here idata empty square brackets, which correspond to the star, and then square brackets mlen, which match the mlen there. And that should hopefully be enough to do that, to work with that. Down below, we have a short bit of code in program unit, we use the module, set up our parameters. Here we aren't even creating them as C types. We let that happen implicitly when we move through to the subroutine when we call it. We create our array, idata, mlen, nlen, integer ij, and there's a short little loop to set it up and put some values in there. Print it out in Fortran order, so looping I to j and then printing out the row. And then finally we call C. So let's quit that and try to build that. So let's just build it the same way as before. C array, compile that to object code, and then let's let's compile the Fortran code and link it against that. It's built, and if we run that, then we get this like so. So our array in Fortran looked like this: 1, 2, 3, 2, 1, 2, 3, 4, 5, 6. So it's going across the top row there. Whereas if we look at it in C, it appears to have been transposed, and that's exactly what you would expect. We've shifted the way that we perceive the array. It can be confusing, and it's something that you always have to remember when you go back and forth between C and Fortran. Certain things like FFTW, particularly I think FFTW, when that was still the version being used, made you really think about this. I don't think you have to think about it quite so much in FFTW3, but if you have any libraries, say, written in one language or the other, and then you have to make calls with arrays across them, you sometimes have to turn your head sideways and make sure you understand the correct array layout. So if you do this, then it does look like the array has been transposed. That isn't the case. It's just that we are looping through it. We are looping through it in such a way that our indices have been changed. The memory itself is the same; it hasn't been changed, and the loop itself is the same. Even we are still moving contiguously from one element of the array to the next. We're just giving them a different set of indices, and it makes it look like it has been transposed. So it's a little confusing, but as long as you remember to give the Fortran and the C inside your interface the correct layout. So if we say mlen and nlen there become mlen, nlen star here, and that corresponds to them this way around here, then that will all work itself out. It's just a matter of making sure to do this swap from here to here, and then to remember that everywhere else you should basically just work as normal, assume nothing has changed, and you'll work in Fortran as though you were just working in Fortran, and in C as though you were just working in C. Okay, I hope that's okay. This can be confusing. I'd say if anyone isn't sure about this, I would maybe I'd maybe have a go at this yourself later on, and just maybe change the sizes, if you like, of mlen and nlen, and really make sure that you can convince yourself that although everything looks like it's been shifted around, it's been transposed, it's actually just the same. Of course, if you do have any questions just now, please do say so, and I'll try to help you out now while I'm actually here. We'll just briefly try to blitz through this very last part here in the 12 or so minutes that we have left. There is another exercise. Let's try and go through pointers. So there's a little bit of extra work needed if you need to work directly with pointers. So we've got derived types which are called C pointer and F fun pointer or fun pointer. That's actually function pointer is what that's referring to. And what you wouldn't do is you wouldn't create these directly. Instead, if you need to pass the pointer to a Fortran object through to a C function, you would use either C lock or C fun lock, and they return either the C pointer or the C fun pointer that point either to that variable or that data object or that procedure. In both cases, they have to be interoperable. There are some helper functions to go along with that, and these work kind of a bit like the normal ones in Fortran. So if you've got two C pointers hanging around, or if you have two C pointers and you want to check first of all if it's associated at all, or if it's associated with a specific other C pointer, then you can do that, and that works. Yeah, so this works very similarly to normal normal associated function in Fortran. CF pointer gives you some ability to go the other way around. So if you've got a C pointer and you need to turn it back into a normal Fortran pointer, this will do that to you. And also a CF proc pointer lets you do the same thing. If you have a C fun pointer pointing to some function or procedure, and you need to turn it back into a normal Fortran pointer, that will do that for you. There's a little bit of thinking to do about derived types. So if you have a Fortran derived type that you want to be interoperable, then it has to map directly to a plain C struct with just interoperable components. So this means that your Fortran derived type can only be a very basic plain old data derived type. It can't be extended. It can't have type bound procedures, and maybe even more strictly, the data objects which are in it can't be allocatable or pointers. They just have to be normal variables or known size non-allocatable arrays. What's more, you also have to add the bind C onto that. So type bind C, and this would then become an interoperable derived type. Putting that bind C on there means that you can't later on try to do another derived type which extends it. You just get a compiler error if you tried to do that. And this leads on to the other way around. So everything we've done up to now has been about calling C from Fortran, but you can go the other way and you can call Fortran from C as well. And as I say, this has been updated a bit in the very newest compilers which are coming out, which are only really just now bothering to implement Fortran 2018 and the like. But let's imagine that we have a C program with a struct, so type def struct of AS, int nlen and float star data, and we call that array t. So we call this an array t type def. And this is really putting an array together with its size. So we're saying it's of size nlen, and here's the pointer to an array of floats, which is going to be of that size. Then let's say in C we can have a Fortran, which we're going to refer to there as f subroutine, and that's going to contain a const array t star a. So we're passing through a constant unchangeable within the function array star. So an array of which we're calling a. So it's being passed by reference. Well, passed by reference, because we're putting that pointer through with it. And then in Fortran, what we need to do is we need to have a corresponding type, which matches the type def in C. So we're going to call it array t again, and inside it we're going to say that we've got an integer c int n len, and then we're going to have a pointer data, which is of type c pointer. So we can create this. Remember, we wouldn't ever put values in it directly. We could either use one of these functions up here, or else we could just get it as an argument, an actual argument directly from a C call. Finally, the subroutine, which we're now intending to call as a function from C, we write like this: subroutine f subroutine a bind C. Again, we've got to have bind C somewhere in there, and we say that that's going to have a type of array t, intent in for its argument a. That matches what we were intending to call from C here, where we passed that in the call signature there, and we're going to have some a pointer data to go with that. So we then call cf pointer a data a nlen. So we get our pointer to the data like so. We extract it from the data in here. Sorry, we extract it from a data and put it into data, and then we just start working with that as though it were a normal C pointer to Fortran pointer to an array. So the information, the C data is of type floats. That's in the declaration of the Fortran pointer used to access it. So this matches here, and you have to get this done. So if we didn't do this, we would never be able to actually work with anything inside A. We wouldn't be able to cleanly access the data inside this. So we have to say, first of all, okay, here it is. It's inside A, but in order to use it in a Fortran way, I guess we need to do cf pointer first to take that pointer out from it and turn it into an object which we can actually use in Fortran itself. Okay, there's a final example here. And again, I think what we'll do is we'll just take a look at it as is, given we've got 3 minutes until 4 o'clock. Apologies, this last section has been a little bit of a rush. If this is actually something important to you and you want to chat about it a little bit, maybe you can please do put something in the chat, and I'll be happy to do that. That actually covers the entire course. If there's anything we've covered and you want to talk about it a bit more, please do say so. I'm able to stay a little bit, but beyond 4 p.m. if you are, and if you do want to talk about anything. Otherwise, though, I'll just go straight onto this solution here, just to talk a little about what it's doing. So we're just looking to really implement this in actual code. So we're going to take the Fortran type and the subroutine and put them in a module. We need to use bind C on everything, as we've said. The C code provides the struct and the extern void, so we have to say that the Fortran subroutine is extern void to make it to let the C compiler know that we're able to call it. So it might look something like this. We bring in our headers, create our type there, say there's a Fortran subroutine out there. We're going to link against it at link time. Until then, just trust that it exists and it works. And we'll just create some stuff. So let's create an array T, set the size of the data in it, allocate it using the slightly messy malloc that C has to use. Just print out some information and then loop through the array, filling it up as we go. Then we'll call f subroutine passing by reference. So to that pointer here, we give it the address of A. Finally, once that's done, we'll just free up that data, set it to null, and finish. Inside the Fortran code, we'll say here's our module, our ISO C bindings. We'll also use output unit as a nice way of printing out to the screen. Here's our corresponding type that matches the C type def. So we make those match each other, and then we just say here's our subroutine. We make sure, of course, that we've got bind C. We make sure that all of our kinds are going to match the C interoperable types, and then we get to work. So we have a data array, which is a pointer, and we need to work out how to use it. So first of all, we'll do this. We'll say, okay, a data is the pointer in C that we want to use. Turn it into this Fortran pointer here, and it's going to be of size n. Right, output units. So we're being careful and making sure we use output units with our write statements, and we just print out first of all what the length is, and then roll through printing out the data along with the element number of it. And that's all there is to it. There are two ways to build this. One way is to compile both of those to object code first, both the Fortran and the C code using the -C flag. That generates these .o object files. And then finally, we can ask the Fortran compiler to link those together and give us the actual a.out, which we can run. Or we can do it in 2 steps only, with a little bit of extra work needed as well. So it's not entirely just simpler, in that we can just compile the C code. So you compile the Fortran code to object, and then compile the C and link it in a single command like this. But if we do that, we also need to tell the C compiler how to deal with the things, with the Fortran link objects inside FOAT.o, because this will have references and callouts to the G-Fortran, assuming you're using the G-Fortran compiler, references to the libg-Fortran library. If you compile with the Fortran compiler here, that's included by default. If you're trying to do it quickly with the C compiler like so, then it needs to be told about it. So you have to do -lg Fortran to tell it how to do that. Okay, and that's actually everything. So apologies, that's a little bit of a rush. but we did make it through to the end. Um, there's no more material, so it's just gone 4 o'clock, and there's nothing else to cover. So I hope that's been informative. I hope that's been useful. It's a lot to take in, but this material will all stay there on the internet, so you can book bookmark it if you like, and come back to check it if you think you've forgotten something and want to brush up on it. I'd also be happy to take emails. I think my email address was probably sent out to you as on the ARCHER2 website. So if you have any questions about this, tomorrow or next week or whenever, and you really do want to know an answer, please do feel free to send me a email, and I'll be really happy to help you out however I can. In the meantime, otherwise though, yeah, I hope it's been informative, hopefully useful for the future, and that's all there is to it. So yeah, I'll be happy to stick around a few minutes if anyone has any questions. Otherwise, thank you for coming, and I hope you enjoy the rest of your day. Thank you. You're very welcome. Very welcome. Plenty to ponder on. Indeed, there is a lot here, and a lot of it's yeah. It definitely has its uses. I think the object-oriented stuff is the biggest thing to ponder on. I would say personally, that's I think likely to get the most use here. Yeah, I hope it's at least fun pondering on.